Welcome to a lecture about the binomial random variable and modeling and approximating real-world events with the binomial random variable. So as we recall, when we talk about an instance of a random variable, we talk about the probability triplet, which is SEP, which is the sample space, event space, and probability space. When we talk about a random variable itself, there's many different ways we can think about it, but we're going to think about it primarily with these 5 ideas. So first, it's the notation for the binomial random variable. That's just a b. It's the parameters, n and p. In the case of the binomial, n is the number of trials, p is the probability of each trial. We can think about the support, which we also talked about for an instance of a random variable. That's just where the variable has, that's where the random variable has non-zero probability. We can talk about the PDF, the probability distribution function, the moment generating function, and of course the 2 moments that we care the most about are the mean and the variance, right? So we've learned these now for the binomial, and we just want to recall what are the rules of the binomial, right? So the binomial rules are independent, identical distributions for its underlying distribution, which is our Bernoulli, right? So each one of those has to be independent, and they have to have the same probability, right? So, and of course, there can only be 2 outcomes, right? There can only be success and failure, so it has to be binomial. This example, you can either think of it as cards or gene expression, right? So in this case, there's 3 genes that are being expressed in some sample. It's gene X, gene Y, and gene Z. And you can imagine inside the cell that there's only 3 genes. Each one is expressed at a different rate. So you can imagine, maybe the cell has 1 million units of gene expression, and 10% of them are gene X, 15% of them are gene Y, and 75% of them are gene Z. Of course, that adds up to 100%. So if we fix X to equal success, and all the rest to be failure, then we have the success probability of 10%, we have a failure probability of 90%, and then we can ask, if we sample at random 10 reads from the cell, what's the probability that we'll see 3 of them being assigned to gene X, which is a fair question. So now we consider a cell of a smaller size, right? It's a fixed size that we know. So we know that inside of the cell, there's 1,000 total units of gene expression or reads, or we can just think of it as 1,000 playing cards. We know that exactly 100 of those are gene X. So if we draw a sample of 100 out of the 1,000 total cards, we model that with a binomial distribution. So we try that, and we look at the probability distribution function for the binomial, and we compare it with this empirical distribution, right, where we actually try having 1,000 reads, sampling 100, and counting how many of those are assigned to gene X. And we see that right here that on the overlay of the distributions, they're pretty similar, right? So it looks like the binomial distribution is a good approximator of this example. However, we can see that the peak probability is a little low. And then we also see that as we move out to approximately 30, you can see in the cutaway that we have sort of excess probability in the binomial distribution relative to the empirical distribution. So this excess probability is precisely why the binomial random variable does not fit this scenario. And you can see that we made a small mistake, right? So to understand why, just imagine drawing a single read or unit of gene expression from our cell, which contains 1,000 reads. So let's draw just 1 read. So if we draw 1 read, the probability that that read will be assigned to gene X is 1 over 10, 10%, right? And we know that because there's a total of 100 out of 1,000 reads, which are assigned to gene X. However, when we draw a second read, if it's a binomial random variable, remember it's IID, so it's independent and identical. So the probability will again be 10%. However, in this case, the probability will be 99 divided by 999, because there's only 99 reads left to draw. So it's a small difference, not much less than 10, but it is less than 10. So each time you draw a read or a card that matches to gene X, the amount of gene X available to draw goes down, which is why it's harder to see 30 reads. Whereas in the binomial distribution, the probability of success stays the same, which is why the distribution has fatter tails. So what we're seeing here is it's close, but not quite. So the binomial works, but it's not actually the correct random variable to describe this phenomenon. So, what is the correct random variable? Well, that's the hypergeometric distributed random variable. So it sounds scary, but it's actually a very straightforward random variable, right? It has more parameters. It has to have a capital N and a capital K. Capital N and capital K is the total amount of options in the universe. So in this case, 1,000 reads in our cell. K is the amount that denotes success. So of course, remember in the binomial, you just have P. Here you can infer P the first time with K over N. Of course, if you draw success, it's going to be K minus 1 over N minus 1, right? So it's changing. So the most common way to think about this distribution is we think about it for playing cards. So people who are playing poker, they're making hands, right? There's 52 playing cards, and you might ask, what's the probability of if I draw 5, 4 of them will have a matching suit, right? So if there's 4 suits, I believe, and each one of those is assigned, in each card is drawn at random. The probability that you have, say a diamond on the first one is 1/4. But then on the next one, it's going to be slightly less than 1/4, right? So initially there's 13 diamonds out of 52, and then to get a diamond on your second draw, there is 12 diamonds, and then 11 diamonds, and then 10 diamonds. So it's getting smaller. In the binomial distribution, which won't make sense in this case, because the binomial distribution would say things like, it's possible to draw 5 jacks, right? Because you could draw 5 cards, and the probability of seeing a jack has to always stay the same. So this is a useful one, but one thing that's important to remember is whenever the data set's big, the binomial looks kind of like the hypergeometric. In fact, the binomial distribution is the limit distribution as n goes to infinity, right? So as n goes to infinity, we can just use k over n to equal p, and we can use the binomial for a hypergeometric going to infinity. Okay, so now though we're going to say, what if we want to use our binomial to model a joint outcome, right? So what's that mean? So let's say, remember we had gene X, gene Y, and gene Z, and we decided to denote gene X as success and anything else as failure. What if instead we want to say gene X, that's sort of success 1, and gene Y is success 2, and gene Z is failure. And we want to know the probability of seeing 10 copies of gene X, 10 of gene Y, and the rest of gene Z, or failure. So we can think of that as a 2-part probability mass, right? So we have to think of probability that K equals 10 and J equals 15. Right, where K is gene X and J is gene Y. And of course, we know that there's that 10% of the reads belong to gene X and 10% belong to gene Y. So we do know that intuitively, at least, that seems like that would be the expectation, right? We expect to see 10 and 15. But we want to model the probabilities around there. Because we wanted to do this in two dimensions, we're actually just going to set gene X to be 10, and we're just going to move gene Y around. So J, move around, and we're going to look at that probability distribution function. And the way we're going to calculate that using the binomial is we're just going to assume the 2 events are independent. Then we can multiply those 2 probabilities together, right? So we can assume, okay, they're independent. So first you see 10 copies of gene X, and you also see 15 copies of gene Y. We can look at that distribution as we shift around J, and what we see is, again, the binomial distribution looks like it approximates this scenario pretty well. Same problem again. We see that at the expectation, which is the peak of both of these distributions, we see the binomial has slightly less probability, and so we assume it must have some excess probability somewhere out by the tails. Again, why is this? Well, you can see that this is because, again, we violated another one of our criteria, right? So the binomial is only supposed to have binary outcomes. This has 3 outcomes, right? Success 1, success 2, success 3. You can't evaluate those separately and multiply them. And so for example, of Y, imagine we're drawing 100 reads. Well, there's a probability that 50 of them, for example, will be gene X. It's very low, but it's possible. Also a possibility that, say, 51 of them will be gene Y. It's also very low, but it's possible, right? So that's our binomial, n equals 100, success probability is 15%. and k equals 51. That has non-zero probability for a binomial because it's possible. So then we can multiply those together. So probability of seeing 50 copies of gene X, 51 copies of gene Y, and that would give us the probability of seeing 51 reads assigned to gene Y and 50 reads assigned to gene X out of 100. That would also be non-zero. However, we know that's not possible because you can't have 101 total reads. There's only 100 reads. So you can't have 50 and 51. So when you evaluate them separately, you're actually overcounting probability where there is no probability. So while it looks like a decent fit, it's not technically the appropriate distribution. And the appropriate distribution is the multinomial random variable. So multinomial random variable is pretty easy to understand. It's just like a binomial, only your probability, instead of being a value, it's a vector, right? So you have k outcomes, you have a probability vector with k probabilities. So this allows us to calculate the joint probability of seeing some amount of one event and some amount of another event in the same total event space. To recap, the binomial random variable, right? We saw that we made two mistakes, right? We violated binary outcomes and we violated our independence assumption. When you do that, you no longer have a binomial random variable. In the case where we violated independence, we saw that it was the hypergeometric distribution. In the case that we violated the binary outcomes, we saw that we need to use a multinomial random variable. It's fine, but also we learned not to sleep on the binomial random variable because the binomial random variable does a good job of approximating both of these other distributions as long as we're not out by the fringes of the distribution. When we're out there, it gives us sort of some funny numbers where we have positive probability for events that we know are impossible. So let's go back to what we mentioned in the beginning of the video about rainfall in a certain week, the amount of days of rain in a certain week. And the link is right here. And what we get when we download this is for every weather station in the country, we have all the weather data going back from 1880, I think, to 2020. So it's a really good resource for us to play with. So what I want to do is see if the binomial random variable can approximate the days of rain over 4 different intervals. So those intervals are going to be a 3-day period, over the course of a week, over the course of a month, and over the course of a year, okay? So of course, the code is all shared, and when we look at the expected probability distribution of a binomial random variable versus the empirical data, this is what we see. So, looks okay, right? We're seeing in gray, we're seeing the expected counts from a binomial sampler. On the top left, what you can see is that the expected amount of rain over 3 days is around 0.5, right? So around half a day. And that's because overall, it rains about 1 in every 6 days in Central Park. We can see that one small issue is it looks like the variance of the real data exceeds what we see in our binomial model, right? We can see that the percent difference in the variance is highest in the time scale of a month. And the most rapid changes in weather occur every single year, right? And so when we're looking at a 3-day interval, and we're trying to model it with our binomial random variable, well, we're assuming again that it rains every 6 days, right? So we're saying, okay, with probability 1/6 that it rains, what's the probability of seeing 1, 2, or 3 days or 0 days out of 3 in a random set of 3 consecutive days drawn from the year? Of course, some of those days are drawn from maybe the summer and some are drawn from the winter, and depending on what season they're drawn from, it's not really a 1 in 6 chance. But again, it's only 3 days. You can only be off by so much. And then we go to a week, we have the same problem. Then we go to a month, and we still have that problem that some months are months that are more dry, some months are the summer, some months have more storms. And of course, when we move up to a year, that problem sort of washes away, right? Because now if we do a whole year, then the amount of days of rain can sort of use that global probability, because it's going to underestimate, of course, the rainy months and overestimate the dry months, which is fine because it'll average out, and it's going to be better to estimate either a very small interval or a very big interval that washes over the monthly or seasonal variation in rain. And that's what we're seeing here. So we're seeing it does a good job, but not a great job. And of course, our main issue with it is that in all the intervals, of course, it doesn't capture all the variance in real data, because real data, invariably has some dependencies. And even if we didn't know the dependencies, we would probably see that variance in real data usually exceeds what we see in a binomial. In this case, we understand that we have this argument about seasonal changes in rain patterns, although of course when we look across the yearly interval, we still see the same problem, which suggests that there's other sources of variance that we're not capturing, although overall the binomial random variable is doing pretty good. So let's recap now. We talked about the binomial random variable. We said one aside we have to mention, of course, is that one reason that some people, especially in the past, didn't use the binomial random variable is that it can be intractable for really large sets of data. Now, obviously today computers are a lot faster, right? But you can still see that to calculate the cumulative distribution function, which to say what's the probability that I see less than 10 days of rain, over where you have 10 million trials, will take you on a regular computer will take you approximately 13 minutes, right? And you can see here that the computational time is moving up, and it's not scaling in a linear fashion, and that's because of those factorials that you have to calculate when you're calculating the probability distribution function, right? Of course, it's not as big of a deal today with computers being faster. However, it's not a quick distribution to work with, right? That's one issue with it. And then the other issue is the variance seems to be a little bit smaller than we see in real data, which makes it not always the best model. Okay, so to summarize, we looked at the binomial random variable, which we've learned about now I think 3 times, but it's a good one. We talked about 2 ways that we can sort of be a little sloppy and try to still use the binomial random variable, and that was to model a hypergeometric random variable and a multinomial random variable. And what we saw was, hey, doesn't do too bad, right? And then of course we saw, despite that, it still has some issues because it seems to underestimate variance in real data, and it isn't the easiest distribution to work with because of that whole n choose k thing. It's not always super fast to calculate. To finish this lecture, we're gonna put the random variables that we've learned about together and talk about how they're related. So now we've learned about the Bernoulli, right, which is a single trial, the binomial, which is a sum of Bernoulli trials, the multinomial, which is the sum of Bernoulli trials, but not Bernoulli. Instead, we've now implied a new distribution called the categorical. So just like the binomial is a sum of binary events, the multinomial is a sum of events that have more than 2 outcomes, right? And so a single run that has more than 2 outcomes, we call that the categorical distribution. It's also, there's a slang for it. Sometimes some people call it the multi-Nulli, which obviously gives you a hint that the multi-Nulli begets the multinomial, just like the Bernoulli begets the binomial. We can see that the categorical distribution is related, of course, to the discrete uniform, except the categorical does not have to have every value have equal probability, right? And then we also know how the binomial and the hypergeometric are related. Given that, we've now filled up half of our world of random variables, and even though it's taken us a few lectures to do that, we've built enough base that by the next video, we can actually completely fill up our discrete random variables. So I'll talk to you guys next time.